Hello friends, welcome to my lecture on review of integral transforms. This is our first lecture on this topic. Let us review two extremely powerful methods to solve the differential equations. The methods are the Fourier transforms and Laplace transforms. These transforms allow us to turn a complicated problem into a simpler one. The idea behind these transforms is very simple. Suppose we want to solve a differential equation with unknown function f, then we apply the transform to the differential equation to turn it into an equation which we can solve easily. This equation is an algebraic equation for the transform capital F of f. We solve this equation for capital F and then apply the inverse transform to find the function f. Diagrammatically, this idea can be represented as you can see this diagram. We are given this differential equation. If you want to solve the find the solution of the differential equation directly, then it is most of the times it is very difficult. So, we apply this transform technique. We apply the transform to the differential equation for the function f and obtain an algebraic equation. This algebraic equation is then solved to get the function f, and the function f is then inverted to get the solution of the differential equation, that is the function f. So, this is a simple idea. Let us see what is the use of Fourier and Laplace transforms, where they are used. The Fourier transform is a tool to find the steady state solutions to differential equations. These solutions may be thought of as the response of a system which has been driven for such a long time that any transient solutions have died out. But in many systems we also need the transient solutions, then the Laplace transform is used. Further, this transform takes into account the initial conditions in a natural way. Let us review the Laplace transform. Let us first define a Laplace transform. Let f t be a function defined for all t greater than or equal to 0, then the Laplace transform of f is a function of s, say f s defined as f s equal to integral 0 to infinity e to the power minus s t into f t dt, provided the integral on the right side of equation 1 exists. Now, this might restrict the values of s for which the transform exists. Existence theorem. Let us see what are the sufficient conditions on the function f so that its Laplace transform exists. Let f t be a function which is piecewise continuous on every finite interval in the range t greater than or equal to 0 and satisfies mod of f t less than or equal to m times e to the power alpha t for all t greater than or equal to 0 and for some constants alpha and m, then the Laplace transform of f t exists for all real s greater than alpha. S could be a complex number. So, this is the existence theorem for Laplace transforms. And it is the conditions in the above theorem are sufficient rather than necessary. So, and it is easy to check whether a given function satisfies an inequality of the form 2, that is the function f is of exponential order or not. For example, consider cos hyperbolic t equal, you can see cos f t equal to cos hyperbolic t is equal to e to the power t plus e to the power minus t divided by 2, and we know that e to the power minus t is less than or equal to e to the power t if t is greater than or equal to 0. Okay. If t is greater than or equal to 0, at t equal to 0 we have f t equal to 1 plus 1 by 2, that is 2 by 2, that is 1. Otherwise, if t is greater than 0, then e to the power minus t is strictly less than e to the power t if t is greater than 0. Okay. So, e to the power t plus e to the power minus t by 2 is less than e to the power t plus e to the power t by 2, and which means that we have 2 e to the power t divided by 2, which is equal to e to the power t. So, cos hyperbolic t is less than e to the power t for all t greater than 0. Similarly, e to the power t, we know it is sigma n equal to 0 to infinity t to the power n by n factorial. So, if t is positive, okay, then t to the power n by n factorial will always be less than e to the power t. Cos hyperbolic t is less than e to power t, t to power n is less than n factorial into e to power t for all t greater than 0. So, they both functions f t equal to cos hyperbolic t and f t equal to t to the power n satisfy the condition of mod of f t less than or equal to m times e to the power alpha t. And if you take any bounded function say mod of f t is less than or equal to some constant, okay, k for all t greater than 0, okay, then it obviously satisfies the condition mod of f t less than or equal to m times e to the power alpha t. Okay. So, for example, you can take f t equal to sin t and cos t, they are bounded by 1. So, all bounded functions satisfy the condition of existence, this condition given in the existence theorem. If f t equal to e to the power t square, then we see that the condition 2 is not satisfied. This condition does not hold for the function f t equal to e to power t square, because howsoever large m and alpha you take, e to the power t square will be greater than m times e to the power alpha t for all t greater than t naught, where t naught is a sufficiently large number, and of course, it will depend on m and alpha. Now, note that the conditions in the existence theorem are sufficient rather than necessary. The conditions given in the theorem are sufficient rather than necessary, because we have functions for which Laplace transform exists even without they satisfy the conditions of this theorem. So, for example, you consider f t equal to 1 by root t. At t equal to 0, it assumes value infinity, but its Laplace transform exists. Laplace transform of t to the power minus half we can find as 0 to infinity e to the power minus s t into t to the power minus half dt. You take s t equal to u. So, s dt is equal to du, and what we get is then if s is positive, okay, then what will happen, the limits of integration will remain t to infinity, t 0 and infinity, and we will have e to the power minus u, t will be u by s raised to the power minus half, and dt will be du by s. So, what we will get is 0 to infinity 1 by root s 0 to infinity e to the power minus u to the power minus half du. Okay. And this is 1 over root s into gamma half. Gamma half is root pi. So, we have root pi over root s, where s is positive. So, Laplace transform of f t equal to 1 by root t exists, but it is not piecewise continuous in a finite interval when t is greater than or equal to 0. You take finite interval say this one, this is your, let us take finite interval to be say 0 to some number a. Okay. So, in the interval 0 to a, it is not piecewise continuous. Now, further, if the Laplace transform of a function exists, it is unique. Conversely, if the two functions have the same Laplace transform, then they cannot differ over an interval of positive length, although they may differ at various isolated points. Practically, it is not significant, hence we shall assume that the inverse of a given transform is essentially unique. The Laplace transform satisfies the linearity property. If f and g are any two functions whose Laplace transform exists, then Laplace transform of a f t plus b g t equal to a l f t plus b l g t, where a and b are constants. Laplace transform of derivative. Suppose f is a function whose Laplace transform exists, and f prime t is piecewise continuous on every finite interval in the range t greater than or equal to 0, then Laplace transform of f dash t is given by s into Laplace transform of the function f t minus f 0. If we denote Laplace transform of f t by f s, then we get s f s minus f 0, and from this result iterating we can get the Laplace transform of f double dash t and more higher order derivatives. Suppose we want to find Laplace transform of f double dash t, then we apply this formula for f dash in place of f. So, then L f double dash t will be equal to S times L f dash t minus f dash 0, replacing f by f dash. Now, S times Laplace transform of f dash t is S into L f s L f t minus f 0 minus f dash 0. So, what we will have S square L f t minus S f 0 minus f dash 0. So, we get Laplace transform of f double dash t as S square into f s minus f f 0 minus f dash 0. We can again use the iteration over this and get the Laplace transform of f triple dash t and so on. So, Laplace transform of the nth derivative of f is s to the power n f s minus s to the power n minus 1 f 0 minus s to the power n minus 2 f dash 0 and so on f n minus 1 0. Now, Laplace transform of the integral of a function. Suppose Laplace transform of f t is f s, then Laplace transform of 0 to t f u du is f s by s. So, when we take the integral of a function, then its Laplace transform gives the Laplace transform of the function f divided by s. Now, let us study two important properties of Laplace transform concerning the shifting on s axis and t axis. In the first shifting theorem, if Laplace transform of f t is f s for say s greater than alpha, then Laplace transform of e to the power a t into f t is f of f s minus a. That means, there is a shifting on the s axis where s is greater than a plus alpha. Now, so replacing s by s minus a in the transform f s corresponds to multiplying f t by e to the power a t. In the second shifting theorem, if L of f t equal to f s, then e to the power minus a s f s is equal to Laplace transform of f tilde t, where a is greater than 0. F tilde function is defined as 0 if t is less than a and f of t minus a if t is greater than a. So, this can be alternately written like this using unit step function L of f t minus a u a t equal to e to the power minus a s f s. If you use the unit step function u a t is defined as 0 if t is less than a and 1 if t is greater than a. So, u a t into f t minus a will be 0 if t is less than a and f t minus a when t is greater than a. So, f t minus a into u a t is f tilde t. Now, differentiation of Laplace transform. If L f t is equal to f s, then let us see what happens when we differentiate the function f s, which is the Laplace transform of f t function. So, differentiation of f s with respect to s corresponds to multiplication of f t by minus t. So, L of t f t is equal to minus d over d s of f s, and when you use mathematical induction, you get L of t to the power n f t is equal to minus 1 to the power n f n s, where this is f n s is the nth derivative of f with respect to s. Integration of Laplace transform. If L f t is equal to f s, let us see what happens when we integrate the function f s with respect to s. So, when you integrate f s, the function f t is divided by t. That is, the integration of the Laplace transform f s of a function f corresponds to the division of the function f t by t. One more property which we have to consider is the convolution. Another important property of Laplace transform is concerned with the product of transforms. Quite often we wish to determine L inverse of f s into g s, where inverse Laplace transform of f s is f t, inverse Laplace transform of g s is g t. So, we know the Laplace transform of two functions f t and g t. We want to determine the inverse of the product of f s and g s. So, it turns out that if h t is the inverse of Laplace inverse of f s into g s, then h t is actually the convolution of f and g, and this convolution of f and g is defined as integral over 0 to t f tau g t minus tau d tau. So, L inverse of f s into g s is the convolution of f n g, that is why we call it a convolution theorem. Now, let us look at periodic functions. These functions occur in many physical problems and mostly they are more complicated than a single sine or cosine function. Let f t be a piecewise continuous function for all t greater than 0 and f t plus p equal to f t for all t greater than 0. Then L f t is equal to 1 over 1 minus e to the power minus p s integral 0 to p e to the power minus s t into f t dt, where s is greater than 0. Let us consider the mathematical model of forced oscillations of a body of mass m attached at the lower end of an elastic spring whose upper end is fixed. Let k be the spring modulus and k naught sin p t be the driving force or input. Then we have the initial value problem, m by double dash plus k y equal to k naught sin p t by 0 equal to 0 by dash 0 equal to 0. Let us solve this equation by using Laplace transform. So, we can write it as by double dash plus k over m into y equal to k naught over m sin p t. Now, let us denote over k y m by equal to omega naught square. So, then by double dash plus omega naught square into y equal to capital K sin p t. Let us take the Laplace transform. So, L by double dash, because Laplace is a linear operation. So, omega naught square Laplace transform of by t and then k times Laplace transform of sin p t. Laplace transform of by double dash will be s square by s minus s by 0 minus by dash 0 plus omega naught square by s. By s is the Laplace transform of by t equal to k times Laplace transform of sin p t is p upon s square plus p square. Now, we are given by 0 equal to 0, by dash 0 equal to 0. So, using the initial conditions s square plus omega naught square into by s equal to k times p upon s square plus p square, or we get by s equal to k times p upon s square plus p square into s square plus omega naught square. So, by s is equal to k p upon s square plus p square into s square plus omega naught square, where omega naught is equal to root k y m and capital K equal to k naught y m. We can then find the inverse Laplace transform. So, what we will do is we will break it into partial fractions and this will be k times p 1 upon s square plus omega naught square minus 1 upon s square plus p square divided by p square minus omega naught square. So, by s can be written as k p upon p square minus omega naught square. So, 1 upon s square plus omega naught square minus 1 upon s square plus p square. Now, take the inverse Laplace transform. So, L inverse of by s is equal to k p upon p square minus omega naught square, L inverse of 1 upon s square plus omega naught square minus L inverse of 1 upon s square plus p square, and this is k p upon p square minus omega naught square, and 1 upon s square plus omega naught square is the inverse Laplace transform of 1 upon s square plus omega naught square is sin omega t divided by omega naught t divided by omega naught, and this inverse Laplace transform of 1 over s square plus p square is sin p t divided by p. So, here we assume that p square is not equal to omega naught square. So, we get the function by t is the inverse Laplace transform of by s. This is by t. So, by t is equal to k over p square minus omega naught square p over omega naught sin omega naught t minus sin pt, if p square is not equal to omega naught square, which is the case of no resonance. The equation 5 represents a superposition of two harmonic oscillations, sin omega naught t sin pt, whose frequencies are the natural frequency omega naught and of the freely vibrating system and the frequency of the driving force, this given by sin pt. So, in the case of resonance, we have p equal to omega naught, and p, when p is equal to omega naught, what we have here, if p is equal to omega naught, by s will become k p upon s square plus omega naught square whole square. So, we will get by s equal to k omega naught s square over s square plus omega naught square, and when we take the inverse Laplace transform of this, we get by t equal to k over to omega naught square sin omega naught t minus omega naught t cos omega naught t. Let us see how we get this. So, L inverse of by s is equal to k omega naught is a constant, we can write like this, L inverse of 1 over s square plus omega naught square. Now, here whole square. Let us remember that, let us recall that L inverse of 1 over s square plus omega naught square is equal to sin omega naught t divided by omega naught. Okay. So, and when we differentiate, suppose we know Laplace transform of f t equal to f s, then differentiation of f s with respect to x s gives the multiplication of f t by minus t. So, what we have, Laplace transform of minus t into sin omega naught t divided by omega naught. When you multiply, when you differentiate 1 over s square plus omega naught square, the sin omega naught t over t omega naught will be multiplied by minus t. So, d over ds upon into of 1 over s square plus omega naught square, and this will be minus 1 upon s square plus omega naught square whole square into 2s. So, what we get, Laplace transform of t sin omega naught t divided by omega naught equal to 2s upon s square plus omega naught square whole square. Now, we want the inverse Laplace transform of 1 upon s square plus omega naught square whole square. So, we have to use a formula which divides the Laplace transform f s by s, and that is the Laplace, if L f t equal to f s, then Laplace transform of 0 to t f u du is f s by s. So, we this means that L inverse of 1 over s square plus omega naught square whole square. This means we are dividing this by s. Okay. So, this will be integral over 0 to t u sin omega naught u divided by 2 omega naught du. We are bringing this 2 here, so that it becomes t sin omega naught t over 2 omega naught, and then this right side becomes s over s square plus omega naught square whole square. We divide this by s, and that means that we are integrating this over 0 to t. Okay. So, now this can be easily integrated, 1 over 2 omega naught, integral of this is what, u sin omega naught u. So, u times minus cos omega naught u divided by omega naught minus 0 to t, derivative of u is 1. So, minus cos omega naught u divided by omega naught du, and here we put limits 0 to t. So, when we put t here, this is t, so we get what, 1 over 2 omega naught minus t cos omega naught t divided by omega naught. When we put 0, it becomes 0, then here we get plus 0 to t. So, 0 to t cos omega naught u by omega naught. So, 1 over omega naught, and cos omega naught u, when you integrate you get sin omega naught u divided by omega naught 0 to t. So, what we get? 1 over 2 omega naught minus t cos omega naught t divided by omega naught, and this becomes 1 over omega naught sin omega naught square, sin omega naught t divide 0, it becomes at t equal to 0, at u equal to 0 it becomes 0. So, we get 1 over 2 omega naught here. So, what do we get? 1 omega naught you can take from here outside. So, 1 over 2 omega naught square. This you can take omega naught square outside. So, what you get there? You get 1 over 2 omega naught cube, 2 omega naught cube, and what you get there? Minus omega naught t cos omega naught t plus sin omega naught t. That is the inverse Laplace transform of 1 over s square plus omega naught square, and this we multiply by k omega naught. So, we get k upon 2 omega naught square sin omega naught t minus omega naught t cos omega naught t. When the input and the natural frequencies are same, we have resonance, which is of basic importance in the study of vibrating systems. The inverse Laplace transform. The Laplace transform can be applied to a wide range of initial value problems. The main difficulty lies in taking the inverse Laplace transform. Usually, we refer to the table of Laplace transforms, but if this does not work, then we use the inversion formula for Laplace transform. So, if LFT is equal to Fs, then Ft can be obtained from this formula. Ft is equal to 1 over 2 pi I integral over a minus I infinity to a plus I infinity Fs e to the power st ds. To obtain this function Ft, the integral is performed along a line parallel to the imaginary axis in the complex plane, such that all the singularities of Fs lie to its left. So, you can see this figure. This is the line AB parallel to the imaginary axis in the complex plane, and this line is drawn in such a way that all the singularities of Fs lie to its left. Now, let us consider the contour C. The contour C includes the line AB and the semicircle C dash, this B C D A, this semicircle B dash C dash. So, integral over AB is equal to integral over C e to the power st Fs ds minus integral over C dash e to the power st Fs ds. Now, we have a theorem. This theorem says that if there exists positive constants small k and capital K such that mod of Fs is less than k times r to the power minus k for every point on C dash, on this C dash, this is R, this is R. The circle is drawn with center at this point of radius R. So, when this R goes to infinity, mod of Fs must be less than some constant times r to the power minus k for every point on C dash, then integral over C dash e to power st Fs ds goes to 0 as r goes to infinity. So, this theorem we shall use in this result. So, what we have here, when we take the limit as r tends to infinity here in this formula, so we get limit r tends to infinity integral over AB e to the power st Fs ds is equal to integral limit r tends to infinity integral over a minus IR, because this is a is a minus IR, b is a plus IR. So, integral over a minus IR to a plus IR e to the power st Fs ds, and this is less than, this is equal to this integral is 2 pi I by residue theorem, 2 pi I into sum of residues at the poles of Fs, and this goes to 0 as r goes to infinity. Y over this goes to 0 as r goes to infinity. So, we have this formula. Okay, so now this is f r, we can say f t is equal to 1 over 2 pi I. Okay. So, this is f t is equal to 1 over 2 pi I. Now f t is equal to 1 over 2 pi I is integral a minus I infinity to a plus I infinity e to the power s t f s ds becomes. So, this is how this is equal to sum of residues of e to the power s t into f s ds, sum of residues of e to the power s t into f s at the poles of f s. You divide it by 2 pi I, 1 over 2 pi I integral over a minus I infinity to a plus I infinity e to the power s t into f s ds will be then equal to sum of residues of e to the power s t into f s at the poles of f s. Now, let us say for example, f s equal to s plus 1 over s into s minus 1 whole square. F s has poles at s is equal to 0, which is a simple pole, and s is equal to 1, pole of order 2. So, let us find the residue of f s at s is equal to residue of e to the power s t into f s ds we have to find. So, residue of e to the power s t into f s at s is equal to 0. So, limit s tends to 0, because it is a simple pole, s minus 0 into f s into e to the power s t, which is equal to limit s tends to 0, s times f s is s plus 1 divided by s into s minus 1 whole square into e to the power s t. So, when s goes to 0, e to the power 0 is 1, and we get here 1, here we get minus 1 whole square. So, we get 1. Now, residue at s is equal to 1, which is a pole of order 2. Now, residue at a pole of order 1 has the following formula: 1 over m minus 1 factorial. Residue at a pole of order m, at a pole z equal to z naught of order m. We have limit z tends to z naught dm minus 1 over dzm minus 1 z minus z naught to the power m into fz. If fz has a pole of order m at z equal to z naught, then we apply this formula: residue at a pole z equal to z naught of fz of order m. Okay. So, by this formula, here we have pole of order 2. So, we get 2 minus 1 factorial, limit z tends to 1, this is s here, limit s tends to 1, d over ds, okay, z minus s minus 1 whole square into e to the power s t into f s. So, s plus 1 over s into s minus 1 whole square. This cancels with this, and 1 over 1 factorial is 1. So, limit s tends to 1 d over ds of e to the power s t into 1 plus 1 by s. So, this is limit s tends to 1, derivative of e to the power s t is e to the power s t into t, 1 plus 1 by s, and then e to the power s t into minus 1 by s square. When s goes to 1, what we get here? So, e to the power t, and then we get t here, 1 plus 1 is 2, and here we get e to the power t, and then minus 1. So, we get e to the power t into 2t minus 1, and therefore, sum of residues is e to the power 1 plus e to the power t times 2t minus 1. So, inverse Laplace transform of f s, okay, L inverse of f s. this is equal to f t, and f t is equal to 1 plus e to the power t into 2 t minus 1. This is the inverse Laplace transform of s plus 1 over s into s minus 1 whole square. Now, let us determine L inverse e to the power minus b root s over s, where b is greater than 0. So, let us take f s equal to e to the power minus b root s over s, then L inverse e to the power minus b root s by s by our inversion formula is 1 over 2 pi I integral over a minus I infinity to a plus I infinity e to the power s t into e to the power minus b root s over s into ds. Now, this integral has a branch point, this root s is here. So, the integrand has a branch point at the origin. So, we take a contour a b c d e f which encloses no singularity. Let us see the contour, this contour we take. The singularity is at z equal to 0, we have a branch point. So, it does not enclose that singularity, and the contour is this a b c d e f a. Okay. So, this contour we take, and then we can write the integral over this contour into parts, integral over a b b c c d d e e f f a e to the power s t e to the power minus b root s over s into ds equal to 0. Okay. Now, what do we notice? Let us notice that this f s, okay, is e to the power s t e to the power s t into e to the power minus b root s over s. Let us apply that theorem which we have earlier stated. If there exist positive constants k and k such that mod of f s is less than k times r to the power minus k for every point on c dash, then this integral goes to 0. So, what happens is that this integral, okay, the integral over b c and f a goes to 0, integral over b c and f a, this integral over b c and f a goes to 0 by that theorem, because mod of f s is less than some constant over s and some constant over r. So, that goes to 0 as r goes to infinity. So, this integral over b c and f a goes to 0, and if you take O c equal to rho, this O c equal to rho and O d equal to epsilon, then 6 implies that integral over a minus I r to a plus I r e to the power s t e to the power minus b root s over s ds and integral over epsilon to rho, this minus 2 pi I is equal to 0. When we take epsilon to 0 and rho to infinity and u square equal to T r, then we come to this, okay, this is equal to this, and then what we use is we use the this result, integral over 0 to infinity e to the power minus u square cos 2 L u du equal to 1 by 2 root pi e to the power minus L square, and the error function of x equal to 2 over root pi 0 to x e to the power minus u square du. Then we obtain that this value of this integral is equal to 1 minus error function of b over 2 root t. So, we get the value of this integral. Okay. So, L inverse of e to the power b minus b root s over s is equal to 1 minus error function of b over 2 root t. Now, the Laplace transform can be used to solve certain types of integral equations also. An integral equation is an equation in which the unknown function, let us call it as y t, appears under the integral sign. For example, let us say y t equal to t plus integral 0 to t y tau sin t minus tau d tau. Then let us take Laplace transform of this. So, Laplace transform of y t we can write as equal to Laplace transform of t is 1 over s square plus Laplace transform of 0 to t by tau sin t minus tau d tau, and Laplace transform by t let us take as by s. So, by s is equal to 1 over s square. Here we use convolution theorem. So, Laplace transform of 0 to t by tau sin t minus tau d tau, this is equal to Laplace transform of by t which is by s into Laplace transform of sin t which is 1 over s square plus 1. So, we get by s times 1 minus 1 over s square plus 1 equal to 1 by s square, and this gives you by s equal to s square plus 1 divided by s to the power 4, or we can say by s equal to 1 by s to the s square plus 1 by s to the power 4. Inverse Laplace transform of by s let us take. So, this is equal to inverse Laplace transform of 1 by s square plus inverse Laplace transform of 1 by s to the power 4, and this is equal to Laplace transform of inverse Laplace transform 1 by s square is t plus inverse Laplace transform of 1 by s to the power 4 is 3 factorial over t cube. So, we get t plus this is t cube upon 3 factorial. So, t plus t cube by 6, because Laplace transform of t to the power n is n factorial upon s to the power n plus 1 if n is a an integer, positive integer. So, inverse Laplace transform of 1 over s to the power 4 will be t cube by 3 factorial. So, we get this by inverse Laplace transform, we get y t function, which is t plus t cube by 6. With this, I would like to end my lecture. Thank you very much for your attention.